The law of conservation of energy states that energy can be transferred from one form to another. We already have the technology to convert sunlight, wind, and water into energy. Imagine what we could do with the energy from sound. For our experiment, we looked into converting noise into energy using a piezoelectric converter. Before we started the experiment, we looked into what technology would be needed to convert noise into energy. We found data on experiments that have been done with piezoelectric materials to test this idea, and we read research found by physicists around the world describing what these experiments have shown and how far we have to go to effectively convert sound to energy. There are hundreds of studies done by MIT, NASA, universities, and physicists, but no infrastructure has yet been constructed for this form of energy conversion. Piezoelectric materials are crystalline structures, and when they're supplied with mechanical pressure, like the mechanical pressure from the vibrations of sound waves, they produce electromotive force, or EMF. This voltage, when connected to a circuit, provides electrical energy. This is known as the piezoelectric effect. As we learn in the unit on sound in this class, sound generates sound waves, which are described with decibels. Decibels relate to us the intensity of the sound waves. So for our experiment, we'll measure the intensity of the noise we're surrounded by every day and see how this noise can be used to create sustainable energy. Noise pollution is abundant. Sounds from noisy traffic, public transport like BART or Caltrains, concerts, jet planes, motorcycles, they all create noise at levels of 60 plus decibels. In theory, there's energy in noise pollution that we can harness using piezoelectric materials to create electrical energy without harming the environment by draining natural resources and using the potential for energy already available to us to power electricity. So we predicted that if we use the piezoelectric transducer in a noise-polluted area, we can convert the ambient vibration from sound into usable energy. Figuring out how to change noise from a polluting source into sustainable energy would be a huge step in the fight against climate change.
So to prove our theory that we could convert sound into energy, what we're going to do is we're going to use a decibel meter and record the average decibel level in the bathroom full of singers. And then we're going to play back that audio to our transducer to see if we could convert it into energy. So, let us commence. Brian. I don't want a lot for Christmas. There's just one thing I need. I don't care about the presents underneath the Christmas tree. I want you for my own, more than you could ever know. Make my wish come true. More than you could ever know. Make my wish come true. All I want for Christmas is you.
Alright, let's get started on constructing the model. The model consists mostly of four main parts: the oscillator, the piezoelectric transducers, the circuitry, and a voltmeter. The oscillator is constructed using a sheet of aluminum. I cut it with a rotary tool to create two prongs, each being about 1.5 inches wide and 8.5 inches tall. I then clamped it between a thin sheet of plastic and two pieces of wood. Next, let's go over the piezoelectric transducer. As stated before, piezoelectric transducers create voltage when vibrated or strained. The applied force causes the silicone molecules within the transducer to experience tension or compression, which changes the polarity of the ion as a whole. This change in polarity is ultimately what causes the piezoelectric transducer to generate voltage. We will be taking advantage of this to generate voltage from vibrations from the oscillator. I attached the piezos to the bottom of the oscillator, and after doing testing to make sure voltage was produced, I began working on the circuitry. One thing to note, piezos generate alternating current, so I needed to find a way to convert this into direct current. To do this, I connected them in series with a full wave rectifier, which converts the current from AC to DC. I then added capacitors and resistors in series and connected these to a voltmeter. Now the assembly is pretty much complete. To test the voltage produced from various sound intensities, I placed speakers 10 centimeters away from the model and played a sound at the same sound level as the ones previously recorded. For sounds with high sound intensity, as in above 90 dB, the model would produce roughly around 0.1 volts.
So we've shown how we use the bathroom choir to generate electricity, but how does that apply to everyday scenarios? Well, I'm glad you asked. To implement this concept in the course of sustainability, we tested this model in different scenarios, whether it be a casual night at a bar, rush hour at a high traffic area, or places where noise is for sure going to be present. What we've done is tested in certain places and played back the audio of its ambience to see if it generated voltage. We've seen it in action with our bathroom choir, with an average decibel range of 93 decibels, producing a voltage of 0.1 volts. We've also tested it in a dining hall on campus, with a decibel range of 68 decibels, however producing a voltage of near zero. We've tested it in a neighbor's garage with a motorcycle revving up, with an average decibel range of 104.9 decibels, producing a voltage of 0.1 volts. We've also tested it in a BART station, having an average decibel range of 84.3 decibels. However, it was unable to produce any voltage. Lastly, we tested it on a street with heavy traffic, with an average decibel level of 82.4 decibels, yet unable to produce any voltage as well. Now, according to our data, it looks like we can produce electricity, but only with a decibel range of over 90 decibels. But even over 90 decibels, we could barely produce any electricity, ranging around 0.1 volts. Now, this still proves our hypothesis to be correct. We can produce electricity using sound. However, we could improve our model even further. We can use Arduino devices to get more accurate results. We could also test out different beam lengths to see if it could affect the output. If we could optimize our model to generate electricity more efficiently, then this model will be another type of energy production that will not drain any natural resources. Noise pollution can be a problem people would normally have to face. But if we could convert something as common as noise pollution into usable energy, then we could definitely utilize this to lower the demand of natural resources. Hence the sustainability aspect. I hope this type of energy production becomes more common. Since we deal with noise every day and it seems pretty natural, using noise as a renewable energy source can be pretty revolutionary. But that pretty much sums up the entire presentation. I hope you guys enjoyed watching the video, and I'd like to thank you all for watching.